10:37 in the morning on June 8, 2026. On the very first day of the new school year, the ground beneath southern Mindanao did not just shake, it tore. A major earthquake with magnitude 7.8 rocked Sarangani and surrounding provinces, with an offshore epicenter located 32 kilometers west of Masim, Sarangani, at an estimated depth of 33 kilometers. It was the strongest earthquake to hit the Philippines since the 1976 Moro Gulf earthquake. Children were walking into classrooms for the first day of the school year when the floor began to move. The air was filled with screams and cries of students on the first day of classes. This is the story of what happened in those terrifying minutes, what the science tells us about why it was not the worst-case scenario, and why everyone living near a coastal trench, from the Philippines to Japan to Chile, needs to understand exactly what almost happened in Mindanao. Let us start with the human toll, because the numbers tell a story of both devastation and something else, something that matters enormously for what comes next. At least 77 people died. Over 1,300 were injured and 31 were reported missing in Mindanao. Across Mindanao, more than 87,000 homes were damaged or destroyed. A maximum the Mercalli intensity of an IX, violent, was estimated by the USGS, with approximately 7,000 people within that most extreme intensity zone in western Sarangani, and an additional 1.51 million people exposed to severe shaking. One of the buildings at the Notre Dame of Dadiangas University in General Santos City collapsed. 3 people died after a wall at a warehouse of Century Pacific Food collapsed in General Santos. In Jose Abad Santos, 7 people were killed and 18 others were left missing due to 2 landslides. These numbers are devastating. Every single life lost matters, and entire communities are now living with grief, displacement, and damaged homes that will take years to rebuild. But here's the comparison that every disaster scientist studying this event keeps returning to, because it reveals something crucial about why this earthquake, despite its enormous power, did not become the catastrophe it could have been. In 1976, an earthquake struck this exact same region. The 1976 Moro Gulf earthquake occurred at a shallow depth of about 20 kilometers along the Sulu Trench, triggering a destructive local tsunami that arrived within minutes, devastating coastal communities and causing the majority of the disaster's fatalities. At least 5,000 people died during the earthquake and tsunami, with thousands more remaining missing. A field investigation revealed that the maximum height of the tsunami was approximately 15 meters. Without warning, about 2 to 5 minutes after the earthquake struck, waves as high as 9 meters reached the shore and inundated communities along the Moro Gulf. About 8,000 people died, including those missing and were never found, making it the most disastrous tsunami to hit the Philippines. Read those 2 numbers side by side. In 1976, a magnitude 8.0 earthquake killed thousands through a tsunami that towered 9 meters high. In 2026, a magnitude 7.8 earthquake, nearly as powerful, produced a tsunami that 5 measured at roughly 1 meter. The earthquakes were almost identical in magnitude. The outcomes were separated by orders of magnitude and lives lost. So what made the difference? This is where the geology becomes the actual hero or near villain of this story. The earthquake was caused by subduction along the Cotabato Trench, a major earthquake-generating structure. A subduction zone forms where one of Earth's tectonic plates slowly slides beneath another. Along the boundary between those 2 plates, friction locks the rock in place for decades, sometimes centuries, while the plates continue trying to move. Stress builds slowly, silently, deep underground, exactly like a coiled spring being wound tighter and tighter. Eventually, the friction fails, and the rock snaps free in a sudden rupture, releasing decades of stored energy in a matter of seconds. The entire rupture process was complete in about 70 seconds. 70 seconds. That is how long it took to release energy that had been accumulating along that fault for years. But where exactly that rupture happens, specifically how deep beneath the seafloor, changes everything about what happens next. This is the critical scientific detail that explains the difference between 2026 and 1976. The June 2026 earthquake had an estimated depth of 33 kilometers. The 1976 earthquake occurred at a shallow depth of about 20 kilometers. A rupture occurring 33 kilometers beneath the surface compared to one occurring 20 kilometers down produces a fundamentally different kind of disturbance at the seafloor directly above it. The shallower the rupture, the more directly and violently it displaces the seafloor itself, and the seafloor's vertical movement is exactly what generates a tsunami. A shallow rupture punches the ocean floor upward or downward with maximum efficiency, transferring enormous energy almost directly into the water column above. A deeper rupture, even when releasing comparable total energy, has that energy partially absorbed and dispersed by the additional 13 kilometers of rock it has to travel through before reaching the seafloor. Less of that energy survives the journey intact enough to violently displace the ocean floor. This is the comparative, realistic explanation for the gap between a 9-meter tsunami and a roughly 1-meter tsunami from earthquakes of similar magnitude. It is not that the 2026 earthquake was somehow gentler. A maximum peak ground acceleration of 173.4 gal was recorded, and numerous landslides occurred in southern Mindanao, with 68 causing damage. The earthquake raised the area's coastline by up to 2 meters and moved it up to 200 meters seawards, exposing coral reefs and other previously submerged areas. The ground itself was permanently reshaped. The coastline of Glan and Jose Abad Santos rose by 2 meters, and the shoreline retreated 200 meters seaward, exposing seabed that had been underwater for as long as anyone can remember. That is the signature of an earthquake carrying enormous energy. The depth of the rupture simply determined how much of that energy converted into a tsunami versus how much stayed contained within ground shaking and permanent land deformation. And this brings us to the most important warning embedded in this entire event, because what happened on June 8th was not the worst-case scenario for this region. It was a reminder of what the worst-case scenario looks like. It was a local tsunami. The onset of the first event occurred 2 to 5 minutes after the earthquake. Definitely, the height of the wave would matter in terms of the number of deaths. The issue here is how people will respond. Remember, it's a local tsunami event. We cannot beat the 2 minutes, 2 to 5 minutes. That is the entire window between feeling the ground shake and the ocean arriving at the shore. There is no time in that window for a siren to sound, for an official warning to be issued through every necessary bureaucratic channel, or for a phone alert to reach every coastal resident before the water arrives. In a region where the trench sits this close to the coastline, the only warning system that actually works in time is the shaking itself. This is why disaster scientists describe the goal as developing survival muscle memory rather than relying on official alerts. 5 has set up tide gauges to warn communities of a coming tsunami, but the agency can only do so much. While 5 is ready to monitor and give warnings, nothing can compare to the vigilance and readiness of local communities. The lesson from 1976 was learned painfully, and it likely saved lives in 2026. The massive devastation brought by the Moro Gulf earthquake and tsunami that followed resulted in a change in the country's disaster preparedness plans. It also led then President Ferdinand Marcos to revise the National Building Code a year after the tragedy and create the National Disaster Coordinating Council, the predecessor of today's National Disaster Risk Reduction and Management Council. 50 years of building codes, tsunami drills, and institutional disaster planning stood between the people of Mindanao and a repeat of 1976. FIVOLCS issued a tsunami warning for the provinces of Sarangani, Davao Occidental, Tawi-Tawi, Sulu, Basilan, Zamboanga del Sur, Zamboanga Sibugay, Sultan Kudarat, and South Cotabato, which prompted the evacuation of all residents and businesses living along the coastline. That evacuation, executed in a window measured in minutes, is the visible proof that decades of institutional learning translated into action when it mattered most. But the science is delivering an honest warning alongside the relief. Mindanao Island is surrounded by 3 active subduction trenches. The Sulu Trench runs offshore on the west coast of the Zamboanga Peninsula. The Philippine Trench skirts the eastern coast of Mindanao. And in the middle, the Cotabato Trench hugs the western coast of the main island. The Cotabato Trench is one among 5 trenches that surround Mindanao Island, the other 4 being the Sulu, Philippine, Sangihe, and Halmahera trenches. This island sits in one of the most seismically active corners of the entire planet, encircled by faults capable of producing earthquakes at this scale or larger. And many of those faults sit close enough to the coastline that the next major rupture could occur at a shallower depth than this one did. The Cotabato Trench and these active faults are capable of generating minor to great earthquakes. At least 7 significant earthquakes with magnitudes ranging from M5.7 to M8.0 affected Sarangani and nearby provinces between 1917 and 2023. A future rupture along a shallower segment of the same trench system, or along one of the other trenches encircling Mindanao, would not need to be more powerful than this one to be far deadlier. It would only need to occur closer to the surface. Now let us turn to what this event demands going forward, because the science here points directly towards specific, achievable actions. The first is structural. Infrastructure losses are estimated at US dollars $9.2 million, with 7,866 houses affected, 1,196 destroyed, and 6,720 partially damaged. Every one of those partially damaged structures now carries hidden stress fractures that may not be visible from the street, but that compromise their ability to withstand the next significant aftershock. More than 2,000 aftershocks have been recorded, with further seismic activity expected, meaning the threat to weakened buildings is not a future hypothetical, but an ongoing, present reality. The retrofitting of older structures and stricter enforcement of building codes is not abstract policy. It is the difference between a partially damaged building surviving the next aftershock or collapsing onto people who believed it was already safe. The second is behavioral. Communities in this region cannot wait for sirens because the physics of a local tsunami do not allow for that luxury. The only reliable early warning system is the human body's own recognition that strong, sustained shaking near the coast means the ocean may already be moving, and that the only correct response is to move immediately toward higher ground, without waiting for confirmation. The third is infrastructure for evacuation itself. Clearly marked routes, accessible high ground, and community-level drills repeated often enough that the response becomes automatic rather than something people have to consciously decide to do under extreme stress are not optional extras. They are the layer of preparedness that converts a 2 to 5 minute warning, window from impossible into survivable. Behind every statistic in this disaster are stories that numbers cannot capture. Doctors continued delivering babies in tents through the aftershocks that followed for days. Teachers, on the very first day, students returned to their classrooms, kept their composure, and guided children to safety amid violent shaking and falling debris. These are the moments of stubborn hope that exist inside every disaster statistic. The human decisions made in seconds that determined whether a frightening day became a tragic one or a survivable one. And the psychological aftermath does not end when the shaking stops. At least 25,000 people remain displaced, including around 16,000 sheltering in 31 evacuation centers, while many others are staying in makeshift shelters outside damaged homes due to continued aftershocks. Families who survived are now living with a fundamentally altered relationship to their own homes, a shattered sense of safety that does not heal on the same timeline as physical infrastructure. Every aftershock that continues to ripple through the region reactivates that fear, a reminder that the ground itself can no longer be trusted the way it once was. This earthquake is being studied carefully far beyond the Philippines. Tsunami warnings were issued across the southern Philippines, as well as in countries across Oceania, East and Southeast Asia. Scientists in Japan, Chile, and New Zealand, nations that sit along their own subduction trenches close to densely populated coastlines, are watching this event closely because the same physics that determined the outcome in Mindanao apply with equal force to their own shores. A trench close to the coast, a rupture whose depth determines tsunami severity, a warning window that can be measured in minutes rather than hours. These are not uniquely Philippine problems. They are the shared geometry of subduction zones everywhere on Earth. The Mindanao earthquake of June 8, 2026 was not the worst this region's geology is capable of producing. The depth of this particular rupture spared southern Mindanao from a repeat of the horror of 1976. But the trench that produced this earthquake is still there. The plates beneath it are still moving. And somewhere along that same fault system, stress is already beginning to rebuild. The question this disaster leaves behind is not whether another major earthquake will eventually strike this coastline. The historical record across more than a century makes clear that it will. The question is whether, by the time it does, enough buildings have been retrofitted, enough drills have been run, and enough people have learned to run toward higher ground the instant the ground starts shaking, rather than waiting for a warning that the physics of this coastline simply will not have time to deliver. At 7